In this video, we will learn how to make a smart energy meter using a Raspberry Pi Pico W board and a current transformer. This energy meter will display real-time data of any load on a web page such as current, power, energy consumption, and cost. In this circuit, the current transformer is used to sense the current flowing through the load. A 200 ohm burden resistor is connected across the current transformer terminals, which converts the current transformer current into a proportional voltage. This voltage is then fed to the ADC input pin GPIO26 of the Raspberry Pi Pico W board. Since the output of the current transformer is AC and swings both positive and negative, we cannot directly feed it into the ADC, which only accepts voltages between 0 and 3.3 volts. To solve this, we use a voltage divider made with two 10 kilo ohm resistors R2 and R3, which generates a stable midpoint bias of 1.65 volts. This bias shifts the AC signal so it stays within the ADC input range. A 10 microfarad capacitor is added between the bias point and ground to stabilize the reference voltage. Finally, the ground of the Pico W is connected to the ground of the circuit, and the Pico's 3.3 volt supply is used for the voltage divider. In this way, the ADC pin safely receives the conditioned CT signal for current measurement. This MicroPython program runs on a Raspberry Pi Pico W in access point AP mode, reads a current transformer on ADC 0 GPIO26, computes RMS current, estimates power and energy, stores energy price in a file, and serves a web UI plus a JSON endpoint for live updates. Each module is used in an obsessive base network socket for the web server, time math for calculations, UJSON URI for persistence, and request parsing, and ADC for reading the current transformer. Wi-Fi access point setup. This turns the Pico W board into a access point so phones, laptops connect directly to the Pico W board. AP.IP config 0 prints the Pico W IP, usually 192.168.4.1. While not AP.active, pass is a busy wait. It blocks until AP is ready. Current transformer sensor ADC configuration and constants. ADC equal ADC26 reads ADC0, GPIO26. ADC underscore conversion factor converts ADC.read U16 0 to 65535 into volts 0 to 3.3 volt. Samples controls have many row samples to use when computing RMS. Burden underscore register and CT underscore turns are used to convert measured burden voltage to primary current. The code implements that conversion. File store persistence energy.json processed unit underscore price and energy underscore WH on the Pico file system so total survive power cycles. Load underscore data returns defaults unit underscore price 8.0 energy underscore WH 0.0 if file missing or corrupted. Save underscore data writes JSON. Errors are printed but not read write. Core functions what they do and why. Read underscore current underscore RMS function. Read samples instantaneous ADC values. Convert each row to voltage 0 to 3.3 volt. Subtract the midpoint by 1.65 volt so the waveform is centered around 0. This requires the hardware bias. Sum squares of the centered samples. Compute mean of squares. Take square root gives B underscore RMS of the current transformer burden voltage. Calculate underscore power current underscore RMS. Multiplies RMS current by voltage underscore RMS 230 volt. This assumes unity power factor, purely resistive load. If the load has a non-unity power factor, you need to measure mains voltage waveform and do instantaneous BT dot IT integration or apply a PF correction. Update underscore energy power function integrates energy using power W multiply time as converted to watt hours by dividing by 3600. Energy underscore WH stores energy in watt hours WH. After updating it immediately calls save underscore data to persist the new total. Calculate underscore cost function converts WH into kWh and multiplies by unit underscore price currency per kWh to get the cost. Web page HTML and JavaScript returns a full HTML page with inline CSS to show current power, energy, and cost. There is a form to set unit underscore price and a form to underscore reset energy. The page contains JavaScript fetch slash data every 2 seconds and updates the displayed values. Web server setup and request flow binds a TCP socket on port 80, listens for one connection at a time. For each accepted connection, it reads up to 1024 bytes of the request and decodes it to text. Then it checks three main routes in order: JSON endpoint, get slash data. If get slash data is in the request string, calls read underscore current underscore RMS, calculate underscore power, update underscore energy, and calculate underscore cost. Sends a JSON response with current power, energy converted to kWh in the JSON, energy underscore WH divide 1000 and cost, closes the client and continues the loop. This is the endpoint the page's JavaScript pulls to update live values every 2 seconds, update unit price by get parameter, uses a simple regex to find get slash price equal number in the request line and updates unit underscore price, works for numbers like 12 or 12.3, reset energy get slash reset. If get slash reset appears in the request, it sets energy underscore WH equal 0.0 and saves. Default serve the HTML page, reads the current values, updates energy, so page visits also count, builds the HTML string and sends it. The whole request handling is wrapped in try accept and prints acceptations to the REPL. The server is synchronized and single-threaded. It handles one client at a time. C1.receive 1024 reads only up to 1024 bytes. Very long request may be truncated, but typically browser get requests fit. Now connect the Raspberry Pi Pico W board to your PC or laptop using a USB cable. After connecting, open the Sony IDE. Under the shell, you should see the MicroPython version, which means the Raspberry Pi Pico W board is successfully connected to your PC or laptop. If you do not see the MicroPython version under the shell, go to Tools, Options, Interpreter. Now select MicroPython Raspberry Pi Pico and choose Try to detect port automatically under the port option. After selecting both, click OK. You should now see the MicroPython version under the shell. If you still do not see it, then you need to install the MicroPython firmware on your Raspberry Pi Pico W board. If you want a complete tutorial on how to install the MicroPython firmware on the Raspberry Pi Pico W board, let me know in the comment section and I will make a full tutorial on it. Now copy the MicroPython code, which you can download from the link given in the description. After copying the code, paste it into the Sony IDE. Then save the code to the Raspberry Pi Pico W board with the file name main.py. Once saved, the code is successfully uploaded to the Raspberry Pi Pico W board. Next, disconnect the Raspberry Pi Pico W board from your PC or laptop. Finally, connect all the components together according to the main circuit diagram we discussed at the beginning of this tutorial. Now connect the Raspberry Pi Pico W board to a 5V DC power source. I am using my old PC SMPS to provide 5V to the Raspberry Pi Pico W board. To measure the current of any load, simply pass the load's live wire through the center of the current transformer. As an example, I am using a 100-watt light bulb as the load, and I have passed its live wire through the current transformer. Next, open the Wi-Fi settings on your smartphone and turn on Wi-Fi. After a few seconds, you will see Pico W underscore energy meter. Click on it and enter the password defined in the MicroPython code. Once you enter the password and click OK, your smartphone will be connected to the Raspberry Pi Pico W board access point. Now open the browser on your smartphone, type the Raspberry Pi Pico W IP address and press enter. You will now see a web page displaying real-time load data such as current, power, energy consumption, and cost. You will also notice an input field with two buttons, update and reset energy. Using this, you can update the energy price according to the actual electricity rate. At this point, the light bulb is off, so the current value is very small. When I turn on the light bulb, then you can see that both the current and power values increases, which means our project is working correctly without any issues. When I turn the light bulb off again, then the current and power values drop back to very small values. If you liked this video, then do not forget to subscribe to our YouTube channel